Okay, this is the second part of the titration lesson. In the last part, we looked at the titration curve for a strong acid reacted with a strong base. And when we analyzed the entities that were in the water, at the equivalence point, we found that it was sodium chloride. And sodium chloride, and when we analyze the salt sodium chloride, is a salt that contains both spectator ions. It does not hydrolyze with water, and so we end up with a pH of 7 right in the middle, a very symmetrical titration curve. All right? What we want to look at next is how we can do a calculation concerning a weak acid and a strong base, and in the end, transposing the data that we find in our analysis to a titration curve concerning a weak acid and a strong base. In this particular example, we're going to be analyzing acetic acid, with this first acid being the acidic H. It's going to react with sodium hydroxide. It's going to do the classic double displacement to produce sodium acetate and ultimately water. All right? Now, in the end, it is this conjugate base that we're going to be worried about. So for our example, we're going to have 10 milliliters of 3 molar acetic acid, and we'll just call that HAC, short form for acetate here. So our C2H3O2 is going to be substituted in as AC. Actually, I might even shorten it up to just be HA like we have been. It's going to be titrated with 0.4 molar sodium hydroxide solution. And what we want to do in a problem like this is determine the pH at various positions in the titration. In part A, right at the beginning, no base added. In part B, after 5 milliliters of sodium hydroxide has been added. In part C, at the equivalence point. We've already seen the equivalence point. Remember, at the equivalence point, all right, the way we're going to solve that is at the equivalence point, the number of moles of acid is equal to the number of moles of base. Halfway to the equivalence point, and this is a very special spot in a titration, especially for a weak acid and a strong base. Halfway to the equivalence point, the number of moles of acid is reacted with half the number of moles of base. So we're halfway to where it is become equalized. And then a final example where we've added lots of NaOH and we've gone past the equivalence point. All right? This one here is past the equivalence point. All right? Okay. So in order to analyze a weak acid and a strong base, we need to get some equations down and some ideas down. So just in general, I'm going to deal with HA and sodium hydroxide, and then that's going to become sodium acetate. Again, this particular thing is going to be the conjugate base and then water. So I'm going to have the acid, strong base, it's going to become the conjugate base, and then water. Okay? Now, we've analyzed titrations before using good old-fashioned stoichiometry. But this is going to take something a little different. This is going to be like our good old-fashioned stoichiometry, but I'm going to treat it a little differently. I'm going to start with a certain volume of acid, a certain concentration of acid, and from the concentration and the volume, and using C equals N over V, I should be able to multiply those and get the number of moles of acid. Now, instead of me doing a mole ratio conversion run, I'm just going to make note of the volume of base used, the concentration of base, and then the number of moles of base. All right? So I'm going to think in terms of those three things. And they all can be calculated and intercalculated by the equation C equals N over V. So what we want to talk about now is what happens after we add some base to the acid. So after the addition of certain volume of base to a certain volume of acid. What's going to happen? Well, there's an important thing that we need to consider here. During the titration, all right, the strong NaOH, that strong base, consumes the HA, the weak acid, and converts it to A minus, the conjugate base. This is the conjugate base. And it does so at a 1-to-1 ratio. All right? So what that means is, for every mole of base that is added, the number of moles of HA declines and decreases until the equivalence point where they've both been consumed and canceled out. Now we need to think about this because before the equivalence point, there's still going to be some moles of acid left. So, weak acid. Before the equivalence point, we're going to have a certain number of moles of acid that takes place after the addition of some base. This little mark right here, this little prime sign, that little mark, it's not a 1, but we use it in physics to mean sometimes the number after. So here's the number of moles of acid before, and this prime means the number of moles of acid after the addition of base. So after the addition of base, the number of moles after is equal to the number of moles of acid that I started with, subtracted by the number of moles of base. So if I have a certain moles of acid to begin with, after I add some base, I'm only going to have a little bit of acid left, and I'm going to get that by subtracting. Now, what that's going to do is it's going to turn that acid into the conjugate base. All right? The conjugate base is over here, this guy, N conjugate base. After the acid has been consumed by the base, it's going to convert it into the conjugate base. So the moles of acid here, after it is consumed by the base, will become moles of conjugate base afterwards. So the number of moles of conjugate base afterwards is actually equal to the number of moles of base added. And that's because for every mole of base added, it reacts with the acid and turns it into the conjugate base. Now, why am I going through all of this? In calculating the pH for a titration like this, in the end, we need to figure out how much HA is left in the water and how much conjugate base is left in the water after the addition of some base. And that's what's going to drive our calculations. The amount of weak acid that's left is actually equal to, then I could do it in 2 steps. I'm going to close on room. But it's actually equal to this Na prime, however much is left, over the V total, how much volume was used. That's going to be equal to Na minus Nb over, now the total volume will be equal to the volume of acid that was in the Erlenmeyer flask plus the volume of base that was added. So that's going to be equal to Va plus Vb. Now this is a very important term. This allows us to calculate how much acid is left and what its concentration is after the addition of some base. I can do the same for the conjugate base. That will be equal to the number of moles of conjugate base after divided by the volume total. The conjugate base, it turns out, is equal to the number of moles of base that were added, and again, the total is VA plus VB. These two equations right here, along with our equations of acids and bases and buffers, are how we're going to solve these problems. Okay? So let's go ahead and let's see if we can solve some of these problems. So, at the start, what we want to do here is we want to make a table. HA plus NaOH. And it really doesn't matter what the products are. It's going to be one H transferred to that NaOH. It's a 1-to-1 ratio. The volume of A, VA, equals 10 milliliters. The concentration of A, Ca, 0.300 moles per liter. And now the number of moles of A. We need to do a calculation. We need C equals N over V, which means N equals C times V. When you multiply C times V, and in this case, it's very handy to multiply milliliters by moles per liter. And if you do that, you end up with a unit of millimoles. And what you're going to get here is 3.00 millimoles. So I have 3.00 millimoles of acid in that particular solution. At the start, there are 0 moles of sodium hydroxide. The concentration is 0.400 moles per liter, but it doesn't matter because the number of moles that have been added is 0. So now let's take a look at what's in the water. Our equations that we just derived, HA, that's going to be equal to the number of moles of A minus the number of moles of B over the volume of A plus the volume of B. And in this case, it's a little trivial. I have 3.00 millimoles minus 0 over 10.00 milliliters, and that gets me back my 0.300 moles per liter. In terms of the A, I haven't added any base. The NB is equal to 0. So A is 0 moles per liter. Okay. So now the question becomes, what's in the water? Well, you'll notice I've got a weak acid in the water, and I have none of the conjugate base. This becomes a weak acid problem. All right? It means that I'm dealing with a weak acid, and therefore I'm going to use the equation to determine the H3O plus using my weak acid equation. So because it's a weak acid and there's nothing else in the water, I'm going to use the weak acid equation. The K for acetic acid, 1.8 times 10 to the minus 5. The concentration, 0.300. Now I haven't had a chance to check my math, but hopefully it's correct. 0.0023 moles per liter. And I can take the negative log of that, and I can get the pH of 2.63. All right? So that's at the start, where we haven't added any base. Let's take a look at the second situation. In the second situation, we've added 5 milliliters of NaOH. Now, because it's the same titration, I'm going to have the same numbers in my HA. 10 milliliters, 0.300 moles per liter. When I multiply those, I'm going to get an Na of 3.00 millimoles. Here I've added 5.00 milliliters. The concentration is 0.400 moles per liter. And if I multiply that together, I'm going to get, what is that? 2.00 millimoles, which means, NB, it means that 2 millimoles of the base has consumed 3 millimoles of the acid. So what's in the water? Well, the concentration of the acid. That's equal to the Na minus the Nb, Na minus Nb, Va plus Vb. That's 3.00 minus 2.00 over 10.00 plus 5.00. In other words, that's 1 millimole over 15 milliliters, and that is equal to, I'm looking at my number, 0.067 moles per liter. How much conjugate base was that converted into? Well, that's equal to NB over Va plus Vb. And if we do that, 2.00 millimoles over 15.00 milliliters. And the milli cancel out, and I get 0.13 moles per liter. Now, what does that mean? It means now I have some weak acid in the water and the conjugate base. Remember from yesterday's lesson, if I have a weak acid and a conjugate base, this is an acid buffer. And that means I have to use my acid buffer equation to determine the H3O plus. And if you recall that equation, that's equal to the Ka and then the Ha over the A minus. 1.8 times 10 to the minus 5. And in this case, it is 0.067 over 0.13. And when I do that, I get an H3O plus of 9.3 times 10 to the negative 6. And that's moles per liter. And then I get a pH of 5.03. The important thing to note is, as I start out my titration and I haven't got to the equilibrium point, I have this buffer region. I have what is called the buffer zone. This is in the buffer zone, okay? And we will look at that on our titration curve in a moment. Okay, let's take a look at the next scenario. C, at the equivalence point. So C is a little different here. Again, I'm starting with an HA, and that's going to be plus NaOH. And I'm starting with 10 milliliters, nothing different. And I still have 0.300, and that's moles per liter. And that's still going to be 3.00 millimoles. Now, at the equivalence point, keep in mind, Na is equal to Nb, which means I can convert this thing, I can put that right over here. I'm going to have 3.0 millimoles of NaOH. Now, the thing that I don't know is the amount of NaOH I have to add. This is 0.400 moles per liter. And again, if I use C equals N over V, I can solve for the V. And if I solve for V, and I got to check my numbers, I'm going to need 7.5 milliliters. Now I'm ready again to check what's in the water. So this is what we do at this point. We always check for what's in the water. The amount of HA. Well, notice, if we're at the equivalence point, 3.00 minus 3.00, it doesn't matter whether it's over 17.5 milliliters. There's 0 moles per liter of HA. It's all been used up. But the amount of the conjugate base, it's all been converted. It's all equal to NB, 3.00, and that is millimoles in 17.5 milliliters. And if I do that concentration check, I get 0.17 moles per liter. All right. So at the equivalence point, for a weak acid, titrated with a strong base, what I have at the equivalence point is no acid, but all conjugate base. So what's in the water at the equivalence point? A weak conjugate base. And therefore, I need my base equation in order to calculate the pH. I need my weak conjugate base equation, because it's a weak base, and I'm going to use that equation Kb. Again, that's equal to the Kb times the weak base. Take the square root. This weak base, by the way, folks, is this conjugate base right there. So now I need to check the chart for the conjugate base K of acetic acid. 5.6 times 10 to the minus 10. And that's going to be multiplied by 0.17. Take the square root. And that's going to get me 9.76 times 10 to the negative 6 moles per liter, which I will then turn into a POH of 5.01 and a pH of 8.99. All right, what does this mean here? At the equivalence point, notice it is not neutral. At the equivalence point, you'll notice it is basic. All right, when you titrate a weak acid with a strong base, it results in a basic solution. It means we need to choose an indicator that will change color at approximately pH 9. All right, and we'll come back to that in a moment. Okay, let's try a couple more of examples here that deal with this. We're going to backtrack now. We're going to go halfway to the equivalence point. This is an important part on a titration curve. We're now getting very good at this because we've done it multiple times. We're reacting it with NaOH. Again, 10.00 milliliters. We're getting the idea. 0.300 moles per liter. This is 3.00 millimoles. And I am halfway to the equivalence point. So the amount of base added is equal to half the amount of acid. I think I wrote that wrong at the beginning of this note. Simply it means I'm going to have 1.50 millimoles. Still 0.400 moles per liter. And if again I use my C equals N over V and I rearrange, I can get the volume, excuse me, and that volume at halfway is 3.75 milliliters. And if I continue with my analysis, my HA is going to be 3.00 moles minus the 1.50 moles over 13.75 milliliters, which you'll notice is 1.50 millimoles over 13.75 milliliters, and that is equal to 0.11 moles per liter. And if I analyze the A minus, it's also 1.50 millimoles. Remember, that comes from the amount of base added over 13.75 milliliters, and you'll notice 0.11 moles per liter, they are the same. Now that's very important. Again, notice we've got weak acid, weak base. This is a buffer scenario again. We're in the buffer zone. We're actually right in the middle of the buffer zone. And if I use the equation for an acid buffer, that is going to be equal to the Ka, concentration of HA over the concentration of A minus. And notice, at the halfway point to the equivalence point, the HA and the A cancel out, and H3O plus is equal to Ka. And I made a mistake over here. This is H3O plus. That's the buffer, acid buffer equation right there. This is very important. At the halfway point to the equivalence point, we can actually use this equation to determine the Ka of an acid. So we could do a titration, not know what the acid is, find halfway to the equivalence point, determine the pH at that halfway to the equivalence point, and ultimately get the Ka. All right, well, let's complete the calculation. H3O plus is therefore equal to 1.8 times 10 to the minus 5 moles per liter. No calculation need to be done. Take the negative log of that number, and we have a pH that is equal to 4.74. All right, and therefore, if we wanted to work backwards the other way, you'll learn in the future that that number is also equal to what we would call the pKa. The pKa. It's related to the Ka. All right, that's kind of neat. Halfway to the equivalence point, we have this special scenario where the Ka is equal to the concentration of H3O plus, which means we can get it from the pH. That's kind of neat. One last example. What if we blow it over the top and we add too much base, or we go beyond the equivalence point? Same analysis. HA plus NaOH. We're not going to worry about the products. Again, 10.00 milliliters, 0.300 moles per liter, 3.00 millimoles. This time we know we've added 10 milliliters of base. The concentration is 0.400 moles per liter. And if we multiply that using the C equals N over V, if we multiply that C and V, we end up getting 4.00 millimoles. Now notice, I have more base than acid, all right? And so what happens? Because the NB is greater than the NA, all NA is gone. We don't have to worry about the Na. It's been all turned into the weak base, A. All right? Now, it's weak. We don't care about that weak base. Actually, in this case, 4.00 millimoles minus 3.00 millimoles means that there's 1.00 millimoles of NaOH left. It's excess. It is this that is going to determine the pH of the solution. So what do we have here? What kind of problem is this? This is a strong base problem. Brings us right back to the very first lessons that we did talking about pH. If I have, well, now I can get the concentration. Concentration of that base, number of moles, 1.00 millimoles. Total volume, 10 plus 10, 20.00 milliliters. If I do that, I get 0.050 moles per liter of NaOH, and therefore 0.050 moles per liter of pure OH minus. So this essentially is the OH minus concentration. I put an equals there. I can go straight from that, taking the negative log to a POH, 1.30, and then ultimately a pH 12.70. And you'll notice we've blown past the equivalence point. We've gone past it by 1 millimole, and we've got this drastic change and this drastic spike in pH. That's a lot of information to kind of digest there, but it is online. You can take your time and you can listen to it again. Excuse me. One last thing I want to talk about here. Let's now bring this into the titration curve situation. When we first started to do our calculation, we started off with a low pH, right? We started off down there with a low pH because it was all weak acid. And then we had this area in the middle here, which was actually made up of some weak acid and a little bit of the weak conjugate base. We know that as a buffer. This is our buffer zone. When titrating a weak acid with a strong base, the pH will initially spike up a little bit until a natural buffer is formed, and we will get this plateauing of the pH. And that's where it's acting as a buffer. An important part of that buffer zone is right in the middle, the halfway point to the equivalence point, all right? And if we were to measure the pH at this point, right here, there's my line, and I were to cut across there and measure that pH would be equal to the pKa. I could actually determine the Ka at that halfway point to the equivalence point. The equivalence point was 20, halfway is 10. If I looked at that pH, I could actually get the Ka. And that's how the Ka is determined for many weak acids. Once we're past the buffer zone, all right, once we're past that buffer zone, just like a regular titration, that pH is going to spike at the equivalence point. But notice now the position of the equivalence point. It's not at a pH of 7, but as we noticed in our calculation, I think it was something like 8.99 or 9, which means now we need something like phenolphthalein to act as our indicator because we want it to change color at approximately 9. Excellent. And then once we continue to add base, that spike completes, and we end up blowing it past the equivalence point, and we end up way up in the basic scenario. All right? So there is an example of a titration curve for a weak acid and a strong base. I'm going to stop the calculation, or I'm going to stop the video there, and I'm going to make one more video to analyze the titration curve for a strong acid and a weak base. It's going to have very similar characteristics to the calculations we just did, and so it should look familiar, except just like many of our calculations, it should be flipped on its head with bases in the place of acids.